Good morning. Good morning, everybody. Welcome back for this another, I think, the first colloquium of the year. Today we will have the talk by Dr. Matteo Guainazzi, and he will talk about dirty dancing speeds in the dusty environment of merging supermassive black holes. So Dr. Guainazzi will be introduced by Isabel.
Good morning, everybody. Thank you very much for being here. I was going to tell you again for a new colloquium, but I would like to say for the first colloquium of the year, for the first colloquium of the second Severo Ochoa project at the IAA. So it's the first of the first. Good. Matteo Guainazzi is a faculty member at the European Space Agency at STEC, the European Space Research and Technology Center in the Netherlands, in a place that I'm not able to pronounce. As I should, Norvik.
It's not needed.
Okay, good. Since 2016, he is a study scientist for Athena and a project scientist for CRISP. In 1996, he defended his PhD thesis in astronomy in the Università La Sapienza in Rome, in Italy, with a thesis called Variability and Complexity in the X-ray Emission of Seafood Galaxies. So very well connected to the object of the meeting these days that I'll talk about later. From 1999 to 2015, he was operation calibration scientist for XMM Newton at ESAC in Villafranca in Madrid. And from 2015 to 2016, he was a calibration scientist for Hitomi at the Institute of Space and Astronautical Science in Japan. As far as his research record, he has published more than 500 publications, among which more than 250 belong to Q, and about 15 as first author, with more than 12,000 citations, or an H index of 58, more than 40 invited talks at international meetings. And he has been PI of several programs for XMM Newton with more than 400 hours, also for Chandra, Susako, and Beppo-Sachs. And he has been member of the Chandra Theme Allocation Committee and from the Chandra Users Committee. As far as the academic record, he has supervised 9 postdocs and about a dozen young research in their initial phases of research as master graduate trainees at ESA and COSOPAR trainees. His main scientific interests in the last few years are accretion flow into supermassive black hole in strong gravity regime, ionization mechanisms of the X-ray in extended narrow line regions in AGN, X-ray obscuration and the AGN unification scenario for radio quiet AGN, accretion disk outflows and AGN feedback, and double and dual AGN. And in fact, today he's talking about this subject, about double and dual AGN in a conference with the title that I like very much, Dirty Dancing. If you didn't realize, Dirty Dancing is there. Piercing the dusty environment of merging supermassive black holes. Mateo's here in the context of the 6th AGN Spanish research that is taking place starting this afternoon here in Granada and will take long for 2 days. And with the title of In the Era of the New Observatory. So it's very well connected with Mateo's activity. So thank you very much, Matteo. It's a pleasure and an honor to have you here. Thank you very much for having accepted their invitation, and the floor is yours.
Thank you, Isabel. Before I start, I have to do that. And okay. So I'm ready now. Thanks for the invitation. Thank you, Isabel, for the very nice presentation. And it's really a pleasure for me to be back at the Instituto Astrofisical in Andalusia after more than 10 years, probably. Too long a time been absent for this lovely place where I have so many friends and collaborators. My talk of today is on ¿Qué tengo que hacer?
Clic en la presentación.
Clic en la presentación. Okay, thank you. So my talk today is on a specific phase of the life of galaxies. We know that galaxies live a certain fraction of their life in splendid isolation, but at some point in their life, they merge. Most of them merge, if not all of them. And when they merge, interesting things happen. The galaxy change, of course, drastically their morphology. And in this nice simulation, you will see at the center a small dots flickering. The supermassive black hole at the center of galaxies started getting ignited, so starting getting active. So we know that the supermassive black holes are hosted in all galaxies, probably in all galaxies, but only in a small fraction of their life, black holes are active. And when they are active, they emit an amount of light which largely overshadow the integral of the light of the stars that compose the galaxy. And at the end of a merging process, a new galaxy is born that brings some resemblance and some memory Okay.
Just check the desplegable.
Yeah.
Okay. Yes.
Yeah. No problem. So, as said, this correlation is seen as an indication of a feedback process whose origin is still by far and large mysterious, which is considered the first indication of coevolution between the accreting black hole and the galaxies. But we actually can do better than that. We can also follow, as a function of redshift, the evolution, the coevolution of accreting black hole and galaxies. And the outcome of this exercise, which is shown here in two different ways, is that indeed we see that the density of accreting black hole along the history of the universe and the rate with which stars are forming galaxies, they actually form the same kind of cosmological trend, both of quantity speaking at the redshift of around 2 to 3. And only if you include the AGN feedback on the host galaxy, you can actually explain, as shown in the plot on the left, the distribution, the luminosity function of the galaxy that you observe, for instance, in optical or ultraviolet. So AGN feedback seems to be a reasonable explanation of what happens in the history of galaxies. But in this context, the importance of galaxy merging is that in galaxy merging, we also know that galaxy merging process is not only that the black hole affects the history of the galaxy, but that also the history of galaxies affect the properties of the black holes. And this is seen in particular if we consider what happens, which kind of AGN are hosted in galaxies that have merging, that have undergone a merging. We see, for instance, that when we have in binary aging, in galaxies that are merging, the fraction of active galactic nuclei is larger, and is actually larger the closer the projected separation. And the merging galaxy create actually AGN with the largest luminosities. So not only it seems to be true that the black holes affect the history of the galaxies, but also that merging of the galaxy, they have an impact on which kind of AGN we observe in the universe. And this makes sense in an evolutionary scenario of the galaxies, where galaxies started as isolated disk galaxy in the splendid isolation of the universe, and they go through an evolutionary sequence where a key moment is when a merging happens, and this merging leads not only to a strong increase of the star formation in the merging galaxies, but also triggers instabilities of the gas in the galaxy that eventually lead the gas to fall in the black holes, and therefore, up to that point, quiescent black holes to transform into an active black hole, so into an AGN. And quasars starts in this scenario in coalescing galaxies, and then once the galaxies enter the merging process is completed and a new galaxy is formed, the power of winds emitted by supermassive black holes, they can clear up the environment of the galaxy and allows the supermassive black holes, up to that point were embedded during the merging process in thick dust and clouds, allows now these winds to clear up the environment and us to see quasars, so AGN as quasars, and the brightly shining sources in the sky at all electromagnetic wavelengths. Up to the point, eventually the process ends with a dead and red elliptical galaxy, where also AGN activity stopped, because no longer fuel is available for the supermassive black holes. So this is the kind of scenario that we want to test with data, and we want to use the dual AGN, so pair of galaxy with supermassive black holes, with active supermassive black hole, as a way to test whether this scenario makes sense or not. There is another reason why we are interested in binary AGN or dual AGN, dual supermassive black holes, on which I'm not going to delve in this presentation. It could be the subject of another talk. I've studied a little bit this problem in the context of future mission of the European Space Agency, which is the fact that once two supermassive black holes emerge in galaxies, they come sufficiently close, they start entering into a bound orbit. And the bound orbit eventually leads to the production of gravitational waves. And in fact, the perspective of studying supermassive merging black holes in gravitational wave is one of the main scientific driver behind the spaceborne gravitational wave missions like LISA, and also of possible synergies with large X-ray observatories like in the future Athena. But that's another story that I'm not going to discuss in detail today. So this is an introduction of my talk, and in the rest of my talk, I'm going to focus on how we use the dual AGN to investigate, test, verify, and falsify these scenarios. And in more detail, I will first try to explain and convince you why studying dual AGN is an exciting observational challenge. It's not easy to identify them for reasons that should be clear in a couple of slides from now. And all the samples that we have available so far are not larger than a few hundreds in the best case, and a few hundreds in many cases of candidates for which the ultimate nature is still to be observed. Then I will go to the description of the prediction that various types of simulations of galaxy evolution make on the properties of dual AGN that we use in order to compare our observation with the prediction of these models. And I will discuss two types of simulations. One are simulation of merging of isolated galaxies. So let's take two galaxies isolated in the universe. Let's put them sufficiently close that they merge. And let's see what happens to the properties of the interstellar gas, to the properties of the AGN, to the property, the rate of star formation in the merging galaxies and in the merged galaxy at the end. And the second type of simulation are truly cosmological simulations that follow the evolution of the galaxy population using essentially first principle recipes. I will, of course, the most of my talk will be devoted into comparing the prediction of simulations with what the scanty observational data we have available now tell us. And at the end, I will try to summarize which kind of predictions are still to be tested by future observations. And instead, in my talk, I will not cover the aspect of very close binaries. I will not discuss gravitational wave sources. This is a subject of a different talk that I could give in another moment. Just as a nomenclature to avoid confusion, there are three terms that occasionally in the literature are not used in a consistent way, and I will try to use them in a consistent way to avoid confusion. We call AGN pairs any kind of galaxies that host both active supermassive black holes. However, the AGN pairs can be dual or binary AGN, depending on the galaxy separation. Dual AGN are pairs of galaxies with a separation larger, say, than 10 kiloparsecs, so larger than a typical galaxy radius. And binary AGN are AGN with whose galaxies have a smaller separation. And the subject of my talk today are dual AGN. Now, why is it difficult to find the dual AGN? Well, this is a fact that will be clear in the next slide, but the very bare fact is that if you take whatever sample of galaxies defined in the optical, in ultraviolet, and you look for dual AGN, so pair of galaxies close enough, and that host the supermassive black holes, active supermassive black holes, the fraction of objects you find is never larger than a few percent in the best cases. And you may say, well, this is due to the fact that the nuclei are so close that it's very difficult to resolve them observational. In fact, only with very deep HST observation, you can really resolve dual AGN, in the images. So there might be other ways to identify a dual AGN. So we know, for instance, that supermassive black holes carries with itself clouds of gas that emits strong optical lines. So since these, in the merging process, these black holes, they are very dynamically, they have relatively large velocities with respect to the line of sight. If I find an optical spectrum with emission lines that are not in the position that atomic physics tells me lines should be found, corrected by redshift, well, that's an indication that black holes are moving very fast. And therefore, these are good candidates for spectroscopic dual AGN. But this is also not the case. In 98% of the cases, objects where we see these anomaly shifted optical emission lines, this shift is actually due to single AGN with strong outflows, warped disk, or any other kind of strange things that happen to the gas in the innermost region of an active nucleus, which is, of course, as you may guess, a strongly dynamical place due to the strong gravitational potential of the black hole. So that's not an efficient way to find supermassive black holes, the optical band. Also, the infrared band is not equally nice, it's not equally efficient. It has been demonstrated that the color of dual AGN are overlapped significantly with the color of stars. So if you think to use a wise color selection, for instance, a typical way to identify isolated AGN in infrared, this doesn't work. This selection technique does not work for dual AGN. Also, radio surveys, you may think, well, I want to find the point sources that are very close in space. So there is nothing better than radio. But once again, you may find in the sky several extragalactic sources where you find the two nice, very well identified radio spots. But, two radio spots in an extragalactic object, in a galaxy, could be the hotspot of a jet, could be lobes, could be, strange orientation effect or knots in a radio jet. So also radio galaxy selection, selection of dual AGN in radio is not efficient. So this is the reason why our samples are still small. These are two histograms of the distribution of the redshift distribution of the largest sample of dual AGN that have been collected so far from recent papers. The left one is from HST samples, so imaging selection in the optical. The right plot is the selection in X-rays using Chandra and XMM Newton. And in both cases, the samples, which are not even actually samples of pure dual AGN, they have lots of potential contaminants. They are not larger than 200. So you may guess that if you have a sample of this size, it's not easy to identify population properties, to identify trend with luminosity, with redshift, with other quantities. But we try. And the reason why these samples are so scanty is a combination of observational effect and some intrinsic time scale issue. Let me start to discuss the latter issue, the time scale issue. People studying the simulating the interaction of galaxies, they tell us that in reality, the fraction of time during the merging process of two galaxies, when the two black holes are simultaneously active, is actually a small fraction of the merging process. So the probability when you look at two merging galaxies, that both merging galaxies have an active nucleus, is actually relatively small. This is shown in the plot on the left side in this slide. You see on the top panel the evolution of a separation of two merging galaxies as a function of time in a given simulation with given properties. I show this just as an illustration. It's one of many different simulations that I could have shown in this context. In the mid panel, you see the star formation rate with some peak whenever the distance between the two galaxies gets smaller. And in the bottom plot, you see the luminosity, the bolometric luminosity of the two supermassive black holes. And you see that only one of the two black holes is always active. So it has a luminosity, a bolometric luminosity of the order of 10 to the 42, which is in a range of a Cipher-like galaxy, not AGN, not very strong, but still easy to be detected at many wavelengths, in particular in X-rays. But the secondary black holes, it gets active only very close before the merging. So the total fraction where I can really see this system of binary, of dual galaxy with supermassive black hole as a dual AGN is just of the order of 10% of the whole merging process. So this is a difficulty of intrinsic in nature. There is nothing we can do for that. But also another thing on which we can do something is the fact that evidence since the early 2000, when the first binary and dual and the triple system were discovered, that actually most of the objects that were discovered originally in X-rays, not by chance in X-rays, they were extremely obscured active galactic nuclei. So these are supermassive black holes that are embedded in very thick clouds of dust and gas. And that's not surprising because we saw in the simulation at the beginning, this merging process of galaxies steer the gas, creating instabilities that helps the gas to fall onto the supermassive black hole. This is the reason why the black holes become active. If there is no gas, they cannot be active. But this gas is at the same time a blessing and a curse. It's a blessing because it allows the black hole to be active, but it's a curse because it prevents you, the light shining from the black hole, from being seen. You have to go through a thick screen of column density of gas in order to be able to see the radiation coming from the black holes. And this actually has been proven at the beginning. It was just an indication from a few serendipitous objects. Now this has been proven with relatively larger sample of AGN that has been, for instance, studied using the hardest X-ray band as a selection criteria. You use an instrument called BAT on Swift that is continually scanning the X-ray sky above 10 keV. This is the energy range which is the least affected by gas obscuration. So you can, in the easiest way, see the AGN shining at the center of a galaxy. And if you look at samples selected this way, and you separate these samples into obscured AGN, unobscured AGN, you see actually that the closer the separation between two merging galaxies, the higher the fraction of merging galaxies. So merging galaxies select preferentially AGN that are heavily obscured. So it's very difficult to find them in optical, it's very difficult to find them in ultraviolet, but they can be found in deep X-ray surveys. And that's why I work in this field, because it's a field where X-ray observations are particularly efficient and rewarding. Now, I show at the beginning a nice video of this interaction of two galaxies. Now, this video is nice, but behind it, more interesting, there is, of course, numerical simulation of how the galaxies and the supermassive black holes in the galaxy behave. And this allows this simulation to provide observables that we can compare with our X-ray observations to see whether this simulation makes sense, whether the prediction of these simulations are reflected in the scant X-ray samples we can collect. And this simulation of isolated merging are very useful because they can reach very high time and spatial resolution, which is very important because everything in this merging process is happening on the scale of a few kiloparsec around the merging black holes. And therefore, if we just look at simulation that average on the whole surface of the galaxy, we may lose many details important to understand the physics of the process. But if this simulation allows us to resolve spatial scales of the order of tens of parsec, they can be efficiently compared with the X-ray observation that essentially probes matter on a similar scale. And you can run several runs of these simulations depending on the galaxy mass, the mass ratio of the galaxy, the relative gas inclination, the gas fraction, the black hole mass, blah, 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 blah. You can make lots of different tests, but all of them converge into one fundamental conclusion, that you should expect that the black holes at the center of these merging galaxies, the dual AGN, they will be obscured by a column density on the average of the order of 10 to the 23. This once again immediately tell you why it's very difficult to find this kind of objects in the optical. And before I go ahead to tell you that this prediction has been beautifully verified by our observations, let me stress that still a typical resolution element of this simulation is 50 parsec. So it's of the order or larger of the expected size of a torus, which means that there are lots of physical details that still this simulation cannot properly reproduce. But still, let's see how this prediction compares with the samples that we have collected so far. And of course, I would not be here to stand in front of you if the results would be a failure, or maybe I would, but I would not have such a enthusiastic tone in my voice. The observations actually validates this prediction, confirm this prediction. I have a few slides here where I show experimental results, and typically I show on the left side the results obtained on AGN selected by this Swift BAT instrument, hard X-ray instrument I mentioned before, and the right plots are typically results obtained by our group using instead the Chandra and XMM Newton. And in all cases, the x-axis is the separation between the two galaxies, and the y-axis are measurements of the obscuration of the active nucleus, either directly measured at the column density or as the fraction of Compton-thick AGN, so AGN with an extremely high obscuration, larger than 24 centimeters square in column density, over the whole center. And in all these plots, red means the position of typical isolated AGN. So these data points are a comparison of how dual AGN compare against isolated AGN. And of course, the story is that isolated AGN are more obscured by now. This is not, of course, a surprise to you. And more interesting and more importantly, because this is a quantitative prediction, the median of the obscuration that we observe is exactly 10 to the 23. So it may be a cosmic coincidence, but we like to see this as a verification that the zero-order prediction of the galaxy interaction simulation is verified by different independent samples of X-ray selected binary AGN. Now, but this simulation, they make more specific prediction. For instance, they predict that when we go to lower separation, we should see an increase of the column density. This is actually shown in two ways in this plot that represents, these are results of simulations, these are not data. So you see here again the expected evolution of the AGN luminosity, top panel, column density, medium panel, and the WISE color in the lower panel as a function of time during the merging of two galaxies with supermassive black holes. And this simulation is essentially summarized in the plot on the right that shows you as a function of projected separation, the expected column density. And if you look at the red data points that represent the dual AGN, you see that one would expect an increase of the column density in merging galaxies with AGN at the projected separations lower than 10 kiloparsec. And we do see this effect. We do see effect once again in two independent samples, the BAT sample on the left, the XMM Newton Chandra sample on the right, two different representations. On the left side, the cumulative distribution of the column density that we observe in the sample of AGN. On the right side, the direct fit of the column density as a function of separation. And in both cases, the message is that the closer the galaxy is, the thicker the gas and dust clouds that the two AGN are embedded in. So the more difficult it is, of course, to find them, but of course, the more matter they have in principle for filling. They are, these simulations, the simulation of interacting galaxies, they cover a very large parameter space. So, I could show you tens of other similar plots showing, specific comparison between the simulation and the data, but probably this is the way to represent the overall global comparison between data and simulation, which I find more effective. These plots represents on the y-axis different galaxy interaction simulation under different conditions, and on the y-axis the fraction of time during which you expect to find the dual AGN on a sample of AGN in merging galaxies. And the horizontal lines represents what we observe in the data using the BAT sample as a reference. The blue line is what you see when the merging galaxies have a very similar mass. The red line, what happens when the merging galaxies have different masses. And the data points represent the prediction of the simulations. And to make a long story short, under all conditions, we see that simulations predict a duty cycle of dual AGN within the total population, which is within a factor of 3 consistent with the observations, which given the fact that, all the uncertainties on the simulation and all the bias on the small sample, it's quite a remarkable result. But we have another way of verifying, of testing, there is another class of simulations whose prediction we can compare with the data, which are truly cosmological simulations. So this kind of simulation that essentially try to reconstruct the evolution of the population of galaxies since the time when they are formed to the current universe, taking into account a certain type of recipes related to the properties of a dark matter halos where they reside, the kind of so-called subgrid physics of the processes that occurs within the galaxy that affect their evolution. Like, for instance, the star formation, the cooling due to the ultraviolet background, supernova feedback, black hole physics, and so on. Now, this is, of course, a much better way of trying to understand how galaxy and black hole co-evolve. The problem of this issue is that, of course, there are lots of not phenomenological, but lots of assumption on the subgrid physics recipes that are used, and therefore, there are lots of scatter in the results, depending on, for instance, the type of AGN feedback that we expect, the type of impact of instabilities of a gas on the star formation. All these kind of subgrid recipes can be pretty different from one simulation from the other, and therefore it's a more indirect comparison against the observations that we have. But it's reassuring that if you look at the right plot, the fraction of pairs that different models, different cosmological simulation predict, and you look at the red, orange, and yellow points that represents the dual AGN population, different simulation, they make rather similar prediction within, once again, a factor of a few as a function of redshift, which means that, they are probably none of them is exactly right, but none of them is absolutely wrong, at least as far as the fraction of dual AGN prediction is concerned. And now this cosmological simulation, they also make specific predictions that can be compared with observation. For instance, various independent simulation indicates that one should find more powerful dual AGN at decreasing separation. So if I have AGN which are closer, those galaxies are closer, the luminosity AGN in the average should be higher. Is this true? Yes, this is true, and this is once again shown with the usual trick of showing on the left side the results obtained with the BAT selected sample, on the right side our results using the Chandra and XMM, and once again we see that when the separation of the two galaxies is lower than 30-50 kiloparsec, we see a clear trend of AGN having a higher luminosity. Now, you immediately see here the effect of having small samples, however. You see that we have, of course, been lots of individual sources in order to create this plot of luminosity as a function of separation. We are actually unable to follow the trend well. This is indeed one of the areas where you would need not samples of tens or hundreds of objects, but we need tens of thousands of objects in order to make really good quantitative comparison between the prediction of the cosmological circulation and the data. So something that, unfortunately, or fortunately for my salary, will need to wait for next generation X-ray missions to be possible. Now, of course, not all things are cleared, even tentatively. A recent result using the HST sample I was mentioning before shows that all the nice trend that I've shown so far of increasing NH and increasing luminosity with decreasing separation, actually they seem to disappear in the HST selected sample when we are at very close separation. So very close to the threshold when AGN from dual become binary AGN, so eventually bounded, gravitationally bounded system. Now, we don't know why this happens. One possibility is that at some point during the process, AGN feedback, so winds maybe from the supermassive black holes, are activated by the strong influx of gas. We know that there is a certain common wisdom that strong subrelativistic outflows from accreting black holes, they are primarily activated when the accretion rate is closer to Eddington. I don't think that this common wisdom is true, but if you would believe this common wisdom, you may expect that at a luminosity higher, we have also stronger winds, and this at some point could create a feedback effect, preventing the evolution of black holes to carry on as they did up to that point. So we don't know why this happens, and this is another reason why we need more sample of closer AGN in X-rays in order to be able to trace a feedback effect in X-rays for reasons that I will show in my last slide very soon. But there are some predictions of cosmological simulation that have been verified basically with HST samples. One is then you would expect that successful dual AGN, so galaxy merging in which both AGN are active, they should have typically, according to the simulation, similar black hole masses. And this has been actually proven by the HST sample, where we actually see that the percentage of AGN host galaxies so essentially a fraction of galaxies with dual AGN is higher when we have a merger mass ratio of the order of 1. And if you have a merger mass ratio, so mass of galaxy closer to 1, you may expect also that the black hole masses are closer to 1. Another thing that you would expect, you remember the relation I showed you at the beginning that correlates quantities related to the size of a galaxy with the mass of a black hole, very tight correlations. But they are actually objects that do not fit this correlation, where you see actually a much larger black hole mass with respect to what you would expect based on the standard correlation. And you expect actually this to happen in dual black holes according to the cosmological simulations. But actually we don't see this effect. We see some excess of the black hole mass with respect to the standard M-sigma relation in so-called strip nuclei, which are essentially galaxies in emerging process whose gas has been almost entirely removed, attracted by the larger galaxy. And in this galaxy, only the black hole with small nuclear star clusters surrounding it remains. But this is still a prediction that has to be confirmed. Last point, there is an indication that dual AGN could actually host preferentially with respect to standard isolated galaxies, outflows, AGN-driven outflows. This has been seen so far in molecular outflows, so using essentially the coolest phase of these outflows. But the interesting point is that if this is the case, this may point to the fact that we should see actually evidence not only for outflows, a large fraction of outflows in this object, but also evidence for disturbed and stirred gas that could inflow. And these outflows and inflows could be actually detectable by future high spectroscopic X-ray missions. Now, high spectroscopic X-ray missions will be the subject of my talk tomorrow, but just as a sneak preview, we may have in the future the capability of measuring outflows and inflows in this system with a new spectroscopy, high resolution spectroscopic instrument in X-rays, even if probably The next one in the pipeline, which is CRISM, the subject of my talk tomorrow, to be launched hopefully in a few months from now, will have a very hard time to observe the evidence of this kind of inflows and outflows, even in the X-ray brightest of the multiple AGN we know in the local universe, which is NGC 6240. Not impossible, but very hard. So that's essentially the end of my journey through the subject. So let me just go through what's, I know that his own talk, much information has been dumped on you, much more, of course, that those of you who are not in the subject are probably, can retain, due also to my, the limited time and also limitation of condensing such a complex topics in 45 minutes. So let me give you just the take-home message in this last slide. The first one, I hope that my enthusiasm convinced you that assuming that galaxy merging is triggering AGN is at least a working hypothesis. I'm not claiming that this is the only mechanism to trigger AGN. We know that AGN could be triggered by so-called secular phenomena, by instability in the host galaxy that happen notwithstanding any merging process. We know that these things happen, so surely they happen in the universe. But my point is that without galaxy merging, our full understanding of AGN triggering remains incomplete. That's why I believe that studying dual AGN is very important for us to understand a key phase in the evolution, not only of the accretion black hole in the universe, but the evolution of the whole galaxy. Now, these are the reason why I find this subject exciting and challenging as an observational astronomer is that they are very difficult to find for reasons that are both related to the timescale issue, so that only a small fraction of the time during a galaxy merging process, two galaxies hosting a supermassive black holes are actually seen as AGN. And also due to observational bias, because we have seen and we have demonstrated now that most of the AGN are covered by extremely thick clouds of gas and dust. So X-rays are the best bet to find larger samples. Now, the prediction of isolated galaxy merging, they match very well with what we observe in the existing samples, both in terms of the average column density that we observe and in terms of the fraction of dual AGN that we observe over the total AGN population. But still, our samples are small. So, as I showed you, we would like to be able to follow much better the evolution of the column density or the luminosity as a function of distance. And this will be possible in real terms at the level matching the accuracy of the simulations only with samples 1 order of times larger than what we have available today. So higher simulation, more data are needed, but also simulation at higher resolution are needed because they don't resolve yet the size of the torus. So the region in the innermost part of the AGN where actually the most interesting phenomena happen. And finally, also prediction of cosmological simulation are so far vindicated by observations. We see an increasing AGN activity with decreasing separation up to a certain point, to a certain distance below which maybe feedback effects confuses the picture. And we also observe that there is some excess stellar mass versus black hole mass ratio, but only in a very small sample of objects for which they're not representative of the whole population. And also we observe a certain indication, anecdotal indication so far, for a preference for equal mass black holes for dual AGN. Now, all this is homework for the future, and in order to prepare this future, we have just been communicated by the European Astronomical Society that our proposal for a special session at the meeting of the European Astronomical Society in Krakow this July has been approved. It will be held for the full day on July 13 in the framework of the EIS, and with the title The Last Kiloparsec, which is, of course, reminds the famous last mile. With this announcement, I stop here and I thanks for your attention, and I'm glad to take any comments or questions you may have. Thank you.
Okay.
Thank you, Mateo, for this nice and very interesting talk. And we have time for a couple of questions. Borja.
Yes, thank you for this very nice talk. And maybe this is beyond the scope because you also talk about the resolution in the scale. But I was wondering, the whole scenario you show us is where the two AGNs at some point, even with the lower distance separation between the galaxies, somehow they, or both of them became Eddington luminosity AGNs, but even higher. So the thing is that, for instance, if we assume an AGN with an efficiency in the accretion, because this has been debated and is really forecast, do we expect a cooling process so brief that could enhance this again this accretion to be again Eddington AGN? Or maybe those are ruled out from this scenario?
Okay, so two answers. First of all, when I mentioned in the galaxy evolutionary scenario, object at very high Eddington ratio, I was referring to post-emerging AGN. So these are actually already quasars in their blue phase, which are emitting for a short phase of their life at a very high Eddington ratio. Typically, the object as a dual AGN that we observe, they don't have extreme accretion rates. As far as we can determine the accretion rates in obscured AGN, they are more object of the order of 1 to 10% Eddington ratio objects. So they are not extremely high accretion rate objects. But this process occurs very fast. So the clearing up of the environment of the AGN after the merging, it should actually happen on pretty fast time scale. Essentially, the time scale required for accretion disk flows to propagate through the galaxy until a distance of the order of kiloparsec, 10 kiloparsec, which is the order of a few million years.
And as a follow-up question, for instance, with these new projects that are working on finding AGNs in dwarf galaxies, do we expect some kind of future too for these AGNs that can be ongoing in merger processes?
On dwarf galaxies?
On dwarf galaxies merging to a massive cut. They have AGNs.
Well, dwarf galaxies, we see them primarily in the local universe. So they have remained a dwarf for the whole, they are still dwarf. So I'm not sure that it will not be my first bet to find clues on the phase of the galaxy evolution related to merging, looking at dwarf galaxy, because they seem to me probably a phase of the evolution of galaxies much earlier than the first merging happens. Because you should have otherwise a relatively unlikely event of a merging of two very small galaxies, which maybe happens, but it's not what we typically observe. We typically observe, what we can observe are Lyrt type of galaxies that have a rather larger star mass. So no, I don't expect that, but it might be my own ignorance, but I don't expect actually these studies will be useful to enlighten the same phase of galaxy evolution that we study with dual AGN.
Elizabeth, thank you very much for your talk. My question is related to the comparison of simulations with observations. When you take cosmological simulation, you're sure that you're having a merger, so you take it and you analyze it and everything, so on. That's great. But when you take observations, how sure you are that you're taking a true dual AGN? Because mergers in the universe may take place in multiple mergers. So maybe you're taking something which has two AGN manufactured, maybe more than two galaxies. So have you looked in simulations whether the case could be?
So, in my understanding is that cosmological simulation, they take this into account. So what they do, they give essentially you predictions of what you observe in terms of dual AGN, notwithstanding what the history was. Because in observation, we don't know if, a galaxy that is merging now is already the result of a prior merging. So I think the comparison with simulation is fair. Now, sorry, the comparison of simulation prediction with observation is there. Now, a related question is, what is the history of this galaxy in cosmological simulation? I don't know. I don't know the answer in detail. So, what is the fraction, for instance, of dual AGN in the simulation that in reality is an history of prior merging? So they were several times dual AGN in the past. I don't have a number now available for you, but surely a fraction of them, they have an history of merging, provided, of course, that there is an efficient mechanism to reconvert a red and dead galaxy into a galaxy that can restart the cycle from scratch, which I think is the main issue.
So do you think that it will have a sense to try to compare the environment of the dual galaxies you're taking in the simulations and in the observed universe to be sure that you're taking galaxies that are in the same kind of merging history?
Yes, this is make lots of sense. Indeed, this is being done by groups that they are actually considering samples at higher redshift and also considering the environment. I have to admit that I don't remember now exactly what the results are. But yes, this is definitely something that is being investigated by other groups, by various groups. In fact, by a colleague that I met in CFA a couple of months ago, whose name I can recover and probably also show you what her results are.
Okay, thank you very much.
I had a question. I was not sure if I understood how you identify dual AGNs from the X-ray observation. Like, do you resolve like 2 points, or is it spectrous?
Yes. Well, it depends on what sample you use. In our case, we use X-ray imaging instruments, Chandra and XMM Newton, and therefore we start from sample of candidates defined in the optical, spectroscopically or imaging, for which you just see 2 galaxies with very bright spot at the center. We look at the X-ray images and we essentially calculate the luminosity of the corresponding X-ray sources. And if they have an AGN luminosity, we believe that they are AGN because, if you see 10 to the 33 error per second luminosity in an X-ray observation of a point source in a galaxy, it can only be an AGN. In the case of the BAT sample, the process is slightly more indirect because the BAT instrument is not an imaging instrument in the hard X-rays. It's a collimator of some kind. And therefore, what you have to do in this case, you go to near infrared, for instance, and for all AGN in the BAT sample, you have near infrared imaging. And from near infrared imaging, you see whether the AGN, which is surely an AGN because it has a very high luminosity in a band where no other process contributes, corresponds to 2 galaxy nuclei. So the process is slightly different, but in both cases, you need a sort of step in imaging, either X-rays or near infrared, to make sure that you are truly dealing with a double system.
I heard a little bit that you were like working for PRISM, for example. I
Yes.
saw that the spatial resolution
It's very poor, yes. What you're going to do with CRISM is, for instance, take NGC 6240. These are 3 nuclei at a separation of less than 1 kiloparsec, which implies at the distance of the galaxy, I think the nuclei are separated a few arc seconds. In fact, one of them is even not resolved by Chandra. So you already know that this is a multiple system. So at that point, you take the spectroscopy in X-rays and you see what you get. And then you interpret the spectroscopy knowing that this is a multiple system. You can't discover multiple system with CRISM due to the PSF. More on CRISM tomorrow.
Questions? What is the range of redshift that you can detect with this kind of system? Because this object is very near, right?
Yes. This is actually, I can probably go back, but I can. Yeah. Essentially, optical sample, they can, with HST, they reach. Yeah. They reach now redshift up to 2.5. X-ray samples are only local. And that's of course an issue because, okay, fine, and I have skipped this point purposely on my talk, but it's quite embarrassing because who knows whether the properties of the X-ray selected sample that we have in the local universe, they have anything to do with objects with a higher redshift closer to the peak of star formation and AGN activities. But honestly, even with Athena, so even with very large X-ray observatories, it will be very difficult to collect larger samples of dual AGN due to the angular resolution. You need probably to reach redshift of the order of 1, or probably surely, you need a sort of super Chandra, so lynx-like a concept to be able to start looking at some dual AGN that you can verify in X-rays at redshift of the order larger than 0 point something. So this is really for 2 generations ahead.
Thank you. More questions? No? Thank you, Matteo, again.
My pleasure. Thank you.